Oh, in, sit down, open up the textbook. Slash, we don't have textbook. All right, y'all, let's get started because if you haven't noticed, I have not finished a lecture yet and I'm tired of doing that. So I'm going to go really fast today and talk much quicker, but no, I'll still slow down. We're going to be finishing lecture 4 because I think we did not finish that, right? And then going on lecture 5 and hopefully we can get caught up, or we'll just continually be just perpetually behind for the rest of the semester. But a few things first. We're already week 3. We're going into week 4. This week has been crazy. I know you guys know that. Just reminding you and encouraging you to stay on top of stuff. We are right here, composition number 3. We have next Thursday, which I think that's the wrong date, probably the 30th. And then we have our exam already on week 5. So just make sure you are not wasting this week and still keeping up to date and reviewing it. You will have a quiz right after this class that will be posted. Homework 1 is posted halfway because apparently you can't view the file. But homework 1 is going to be posted, and after today, you should be able to know all the information to start working on that. There's 5 questions on that. It'll be due Friday at midnight. So that's the Friday, the 31st, I think. No, yes, 31st. And then our quiz 2. So we have those 2 assignments coming up. The only really other thing on the radar here is if you are interested in going to the ASCE Student Symposium in Athens, Georgia, at the beginning of March, please come to this meeting on the 2nd floor ASCE space. I don't remember the lab room, but just walk on the 2nd floor of building 4 and you'll hear a bunch of people and you'll smell dominoes and just go in that room. If you're interested in going and you want to go and you're planning on going, then you have to come to this meeting. You can sign your sign insurance forms and stuff. Okay. The other thing I'm just going to mark it here before one last time is this NEFBA cornhole thing that should be fun and free food and free alcohol if you're into that thing. All right. So this, do you need this back?
Yeah, thank you.
I'll post this on Canvas too, but yeah. So if the QR code doesn't work. Okay, all right, so the last few lectures we've been covering kind of the same thing, right? The phase diagram, how to plug in all the things on the phase diagram, how to problem solve based off of what we're given, and then the whole purpose of that phase diagram is to calculate index parameters that are then used in the mechanics, which then allow us to do math and do predictions and get paid as engineers. So that's the big picture of our whole career, which is why these things are important to begin with. So I'm going to start on this sheet, even though I've already talked about this a lot, but this is going to be one of those sheets where it is very helpful to know all of these things. On the FE, you might be just given S value and you need to know its degree of saturation. An E value, you need to know its void ratio. So some of them are intuitive, some of them are not, but I would recommend being familiar with these symbols, the definition, as well as the typical ranges over there in that column. Because as I've said several times, not all of them are intuitive, i.e. moisture content being 0 to infinity %, having a percentage higher than that. Okay, so I know we've been all over the place, but again, like we've gone over these different examples of phase diagrams, and I don't want to confuse you guys by all of these different alternative solutions, assuming this, assuming that. At the end of the day, it doesn't matter like which way you solve it, as long as you fill in the blanks of all of the phase diagrams. So I'm not going to ask you on the exam, like solve it using this, assuming this kind of thing. We have not done this one. This is where we ended off. Maybe I got like one slide in or something. I don't remember. But example number 2, wherever this is, we are going to start back with this one here. So we're given certain things. We're given void ratio, moisture content, and then dry or the specific gravity of solid, or sorry, the density of solid. This is really important too. It always, like, I told you like highlight or underline the units, right? So you know what correct density to use. But also like make sure you're looking at the subscript there too. Because this is not density of dry soil. This is not density of like the bulk soil or saturated soil. That S means the density of our solid portion only. So just this right here. Basically, this is saying this divided by this. So it's not total. And I see that a lot on the exams is you'll see that S and think saturated, but it's not. It's gamma stat or rho stat for saturated. So the whole reason we're given this little number right here is so we can calculate the specific gravity of our solid. Luckily, since the density of water is 1 megagram per cubic meter, this number is exactly the same. We just chop off the units there and it's 2.65. Some of this is repeating. I'm just trying to bring us back up to speed here with that. Scam like you. So what we are going to do with this, since no volume is specified in this, we'll do a assumed volume of solid of 1. And the reason why I said this is helpful is if we're given a void ratio, then this allows us to calculate the volume of voids right away, because we know void ratio is volume of void divided by volume of solid. So if we assume a volume of solid of 1, just 1 unit, whatever that is, in this case, 1 cubic meter, then boom, we can find our volume of void right away to be 0.62, because that's what our void ratio is. Okay, so we have this out already. I'm just going to fill this in, and you may have already filled this in last class, but I'm just going to put it here. Again, our void ratio is 0.62. We know that this is equal to our volume of void divided by our volume of solid. Therefore, we can find our volume of void be 0.62 cubic meters. So that is this section right here, our volume of void is the volume of air plus the volume of water. Also, since we know the volume of void, now we know the total volume. Because the total volume is the volume of solid plus the volume of void. So this is 1 plus 0.62, which is 1.62, which we ended or talked about like in a very helpful equation there that will, includes the void ratio, and I'll go over that again here in a second. So now we basically know everything on this side, or some of the important things. We can go from volume to mass, since we need to find our total mass. So we can find our total mass because now we know our, all right, so we can find the mass of our solid portion. Let's see what was right order I did that, yeah. So the mass of our solid portion is going to be 2.65 megagrams because we assumed a solid of 1. We can find that one on that side, and then using our moisture content, yeah, we can find the mass of our water. Because now we know mass of solid, we know our moisture content is just the mass of our water divided by our mass of solid. Equal to 0.3. Okay, so we found these two, massive solid, massive water. Our total mass, move it up here, just right bigger. It's obviously our mass of our water plus our mass of our solid. Okay, so really take like these homework problems like serious, because like I know following this, like it makes sense logically, like when somebody's writing it out, but really like it is a different animal when you're starting from scratch and like needing to figure out that first like line in the Sudoku thing per se, you know, like before you can actually then fill in the rest. Yeah.
Why are we assuming that VS is one instead of VT is one like the before? And like, how do we know which one is?
That's a great question. Yeah. You could probably still solve it assuming VT is one too as well. So that might be like a thing like you could try, you know, or like on the side is like try solving it with VT equals one. In this case, you get different values for everything. But at the end of the day, your dry density, total density, and all of these would still be the same. So there's different ways to go through it. What I was highlighting with this example is the simplicity of assuming VS equals one in this case because of the void ratio. So this would be like, I mean, usually if you're giving void ratio and you're not given a total volume or you're not giving a total mass, then assuming a VS of one is going to be the easiest way to do it, but it's not the only way. So yeah, we have everything on the mass now. If we need to find our volume of water, what we can do then is, since we have mass of water, we can go backwards to the volume of water then to find the volume of water, sorry, backwards to find volume of water. Since we know our total volume of voids, we can then use this to find the volume of air. Again, if all these equations and all this like arithmetic gets confusing, just look at the arrows, like you know, look at the arrows and see, okay, these two things add up to this one, or I can subtract this parameter from this thing to get the other thing. You know, it's all just kind of visualizing there. So, all right, we have everything set up here. Now, what we're going to do is now we can find our all of these values. So on the next page here, we have these all plugged in. Let's look at the dry density. The dry density is the mass of the solid portion divided by the total volume. And then again, just physically what that means is there's no water. So the water is being removed from it. The only thing that has mass then is going to be the solid portion because the air, whereas already assumed, does not have mass in it. So this is once we take it out of an oven or whatever, we just ensure there's no water. And what is helpful with this now is since we know that the mass of the solid portion is the density of our solid portion times the volume of solid. And I said this last time, since we assumed and made this initial step of the volume of solid being equal to one, this means that the total volume is really just one plus our void ratio. So numerically, hopefully that checks out, but also looking at it here, total volume, if we look at this and the two things that are filled with this, we have our volume of solid and then our void ratio. So the total volume is just one plus this void ratio. Now taking this portion here, all right, I have a bunch of arrows going here, and then this portion here, we can say that the dry density is equal to all right, color changed apparently. I'm not gonna try to fix it because I'm gonna mess it up. Is equal to this over 1 plus our void ratio. Of course, this is times 1. One plus our void right here.
Is the what represent on the top?
The 1 represents the volume of solid that we assumed was 1.
Okay.
Got it. Volume of solid. So technically this is, yeah, cubic meters. So this is nice. This makes this relationship hold true here, where if we know our density of our solid portion, and we know the void ratio, then we can calculate the density of our dry density right through this. And this works either way. So this will work also for the unit weight, if we had unit weight instead. This will also work here. So the cool thing about this, and next week we'll see, is like this value, the density of solid. How can we find this like in the lab?
You put it in an oven, sort of.
That would be for the dry density, like to find the dry density. But remember, this density of solid is just equal to the mass of the solid portion divided by the volume of the solid portion. So it's basically just like the density of the rock, like the quartz or the material itself. So it's more so a material property rather than like a soil property. But we find this through the specific gravity. Because specific gravity, put a little cross right here. Specific gravity is just the density of solid divided by the density of the water. And if you see, fast forward or spoiler alert for next week, we have a really easy lab experiment that allows us to find the specific gravity of the material. That's kind of cool. Like I mentioned this before, specific gravity is like a low-hanging fruit kind of experiment. And if we knew the specific gravity, then we can calculate the gamma solid. And if we know the gamma solid and void ratio, then we can calculate the dry density. Or other way around, if we know the dry density and the unit weight of the solid, then we can estimate the void ratio. So think about this as an engineer, like all of the, like to find these variables, it costs money or it costs your client money because you have to either make an assumption or you have to do an experiment for it. So this is a really helpful tool that allows us to relate these two and potentially save your client money, which will save, which will give you guys more work or, using some, like help develop your business a little bit more by using these correlations here. So let's just do the math out real quick, just for fun here. So using this equation up here, we know that the density of our solid portion is 2.65, and I'm just going to put the units in here just and then we're doing 1 plus our void ratio of 0.62. So we see the only two things that have units right here is, or only one thing has a unit, megagrams per cubic meter. This is unitless, this is unitless. So when we have that right now, the, what is the answer? right here. That would be our answer for this. What you can see is there is there's an experiment out there to find or to estimate the void ratio of soil. Like, and there's also an experiment out there to estimate the dry density of soil. And so like you could be taking engineering time, you could be using lab time, or you could do one, find the specific gravity of our solid and then estimate the other based off of that. Okay, let's look at the same thing here, but now for our total density. We're going to be looking at the total density here on this one. So our total density is the mass of the total versus divided by the total volume. And what we know that the total volume is 1 plus E. We also know that the mass of, sorry, that is not correct. That should be mass total. Okay, yeah, sorry guys, let me make this edit right here. This should be mass of total is equal to mass of, pretend this is a W plus the mass of our solid portion. So we can find these two variables, mass of solid and mass of water, by relating them to the density of solid that we just talked about, and then also the moisture content. Remember moisture content. Right here, make sure you like recall those two connections there. All right, so our total density from right here is right here. Yo, everything okay? Sorry, this is an echoey room. I can hear you picking up in this, so I don't want it to be like broadcast forever. All right, so we have these two things. And we're plugging them in, and I know this is a boring proof here, but what at the end of the day, what we get is that the total density is equal to the density of our solid plus 1 or times 1 plus our moisture content divided by 1 plus our void ratio. So we can plug this in, doing whatever, we have the equation here. But this equation is another helpful universal correlation between all of our variables here. Remember, this is total, because there's no subscript. But we see it also works for the density, so bulk density or moist density or whatever you want to call it. The two of our solid portion, 1 plus our moisture content over 1 plus our void ratio. And so today we did the moisture content test, or you will tomorrow, or whatever, 24 hours, get the sample from it. Also, some of you guys had mentioned there's also something called a speedy test, which you go out in the field and you can actually find the moisture content like on the site, like in an hour, less than an hour or something. Heats it up out there. So we see like gamma S we found, or we can find from specific gravity, low-hanging fruit. Moisture content is also a low-hanging fruit lab test, very cheap to run and very easy to do. So it's another one that will help us correlate some of these density values with some of these variables that are easier to obtain. So this one right here, remember we have this similar equation from the last page, or from last slide. This is the dry density relationship. So we can rearrange this equation to show here as gamma solid is equal to PD or gamma dry times 1 plus E. And sorry, I'm saying gamma, it's rho, but just no density. It's the same thing. I'm using those interchangeably. Density is rho, unit weight is gamma, same thing though. So if we plug this here into our equation down here, then we get this term. Now you can see, hopefully, that these two terms will cancel out because of math and how math works. So those will cancel out. And then boom, we have this beautiful relationship that we use quite often. And maybe you used it last in CE materials when you guys did the Proctor test, I think. But what this does, we rearrange this to see or to show that our one plus our moisture content. So this is maybe the form that you saw from that last lab, if Dr. Hassan did it correctly. So we have the dry unit weight of our material is equal to our bulk unit weight of our material divided by 1 plus our moisture content. Again, the moisture content, low-hanging fruit test. Our bulk unit weight might be easy to find because we have a set volume and we fill the material up with that. But we use dry unit weight a lot of times because we can't trust the water. It could move in and out of it. So we would use that dry unit weight. So that's why this is that's the derivation of this equation here. So to follow along with the example here, this is the thing I asked you to solve. So for the dry density, or total density, let's just put this here, continue on. Okay, so the second to last thing is the moisture content when it is 100% saturated. Yeah, so the moisture content when it's 100% saturated. When this is 100% saturation, this means the voids are completely filled with water. So essentially what we need to do in order to calculate our moisture content when the degree of saturation is equal to 100, we have to find our mass of water with this little asterisk here. When our volume of void is equal to our volume of water. The mass of solid portion is not changing. So it's going to be 2.65. But this is a what if scenario. And this is hopefully kind of intuitive. Like this would be something common in geotechnical engineering. Because again, the groundwater table is going to change a lot. So maybe we need to find a certain soil behavior whenever the saturation is 100%, whenever there's a flood or whenever there's extreme rain events or something. And so maybe we need to find a soil property, a volumetric property like moisture content when we have this specific scenario. So all it does is just take a little bit of extra thinking here, but we would need to say, okay, right now in our current state, we have a mass of water of 0.398. But what would happen if all of this air became water as well? So what would happen when our volume of void is equal to our mass of, or is equal to the volume of water? What would be this new mass of water in a special scenario here? So we know the volume of void is 0.62 because that is our void ratio, and that's what we have on our phase diagram. So to find this new mass of water, we would just take the density of water times this volume of void. Luckily, at the very beginning, we wrote down the density of water, the 1 megagram per cubic meter, which makes our life super easy. Just being super redundant by writing this in, but you guys see. So this new, like, what if mass of water is just 0.62 megagrams. So this what if situation of moisture content when our degree of saturation is 100%. That's this what if moisture water mass divided by the mass of solid, that's not changing. We have 0.62 divided by 2.65 megagrams. We'll multiply that by 100% to show it in percentage form, and it should be 23.4%. This type of question can be like kind of daunting at first because like you need to think of the physical like situation, like what is happening to our soil. So it could be asked either way, like what happens when the degree of saturation is at 100%, or what is the new moisture content when the degree of saturation is 75% or 50%, or anything in between. You can calculate that. You just need to know how much of the air or how much of the volume of void is now going to be considered water. You just have to think like pseudo, like how could this void or how could this phase diagram change? Okay, the last part here, this density when it is 100% saturated. It's basically the same thing we just did with this pseudo mass of water. We know this will be our mass of our solid portion plus this pseudo mass of water divided by our total volume. I'm just going to be redundant here, but this mass of water our volume of water is equal to our volume of void. Which we just found on the previous page to be 0.62 megagram. So we have 2.65 plus 0.62 megagram divided by our total volume, which is 1.62. And this is equal to 2.02 megagram per cubic meter. One of the things that we could do though with this as well, like doing the math out this way is completely fine. But recall from like 15 minutes ago, we found this relationship here where our density is equal to the density of our solid times 1 plus our moisture content divided by 1 plus our void ratio. So we just found this relationship here. And this density right here is just bulk density, meaning it has some amount of water into it. So what we can actually do is, like, let's say if we need the saturated density, then what we can do is just say, all right, well, let's put saturated here. And what that will do is change this moisture content to the saturated case for moisture content. So we can use this equation, solve this. So it's the same equation, it's just taking a different form. And since we just found this moisture content to be 23.4%, I think, yeah, 23.4%, we could actually plug this in and see that 1 plus 0.12 or 2.234 times the density of our solid divided by 1 plus our moisture content will get us the same value here. So this property right here, or this correlation or relationship, whatever you want to call it, between density, moisture content, void ratio, and density of solid is really helpful because the void ratio isn't changing, the density isn't changing, but if we change our moisture content, then we can find whatever type of density we have with respect to that change of moisture content. Because think about it here, like what happens if we have no moisture at all? What would be the moisture content? Like 0. Yeah, so put a 0 right here. So now it's 1 plus 0, so it's just 1. And that means our dry density is equal to our density of solid over 1 plus our void ratio, which if you scroll back 2 pages or 2.5 pages or whatever it was, that was that first relationship that we brought up. You can see how moisture content is related into that. And once we add moisture to it, then we don't have dry, but we have something between like moist and saturated. And this is like a scale where we can calculate them in between. Okay, I'm gonna skip this page because it's the same page as before. I just included it before, but again, just highlighting, print this out, put it in your mirror or whatever. So the relationships we know so far, we know dry density, and we found this cool one here. Helpful. We know the void ratio. Like the actual calculation is volume of void divided by volume of solid. If we know porosity, we can relate it to porosity, or if we know void ratio, we can relate it vice versa. Either way, those two are very related. We know the degree of saturation is equal to volume of water divided by the total volume. And for total density, what we know now, I'm not writing those out. So for total density, we have a couple different relationships that we can add. So the solid 1 plus our moisture content divided by 1 plus our void ratio. We also have this one where it's dry 1 plus our moisture content. And then we have a certain case if it's saturated. All we need is the moisture content in this specific case when it's 100% saturated, or if it's 100% saturated, divided by 1 plus our void ratio. So these are some of those, you can use them as checks, you could use them as quick calculations, but these are some of those equations that relate these volumetric properties. Hopefully you can see a trend of some of these, like this is why moisture content is really important in soil, and this is why void ratio is really important in soil, as well as specific gravity, because specific gravity is used to calculate our density of solids. So a few things I want to note about these equations, though. Must be in decimal form for these to work. You can't put this in equation form or in percentage form. So it has to be the moisture content has to be divided by 100. Just get used to always doing that. Like we do percentage to show, and then for calculations, you divide it back into decimal form for calcs. The other thing of note too is this dry density. It's basically that you can replace dry or density with unit weight in this equation. And why can we do that? Because in order to go between the two, you just multiply by the acceleration due to gravity, that coefficient or that constant or whatever you want to call it. But we're doing that on both sides of the equation. So both sides of the equation, if we multiply the left side by 9.81 or 32.2, and we multiply the right side by 9.81 or 32.2, those they just cancel out. So just boom, you can use these interchangeably here. All of these three equations, if it's shown in row in a textbook or in my notes, just know you can use the density too, or the unit weight as well, the gamma. Okay, there's one more thing I wanted to show for this here that is super helpful. So with this, and maybe you've already heard of this before, but can there be a relationship between all of these parameters that help us? And this is, again, the benefit of assuming this first point here. So if we assume the volume of solid is equal to 1, this means our volume of void is equal to our void ratio. And I'd said before, like using density for the solid portion, then we can find the mass of solid, and then the mass of water too, using this. And here's the mass of water being equal to the moisture content times this. So the degree of saturation, if we know that this is, okay, the degree of saturation, this is the volume of water divided by the volume of void. So we can rearrange this equation to show S times the volume of void is equal to the volume of water. Here we can just do S is equal to the volume of void. Now, right here, we said the volume of void is equal to the void ratio. So we can say that this is equal to the volume of water is equal to the S times our void ratio. And we also have the volume of water being equal to make sure I'm writing this correctly. Yeah. So on this side of the equation right here, times the volume of solid. How we get between this and this is just the density of our water, or density of water times S times E. So since our volume of solid was assumed to be 1, what we get is the other thing that we know here is that GS is equal to the density of our solid divided by our density of water. Let's just go ahead and move this or divide this over here. We can put that over there. Basically what we get, and I'm sorry guys, it's out of order here. I'm going to draw a bunch of arrows everywhere. Basically what we get is this equation. Specific gravity of our solid times our moisture content is equal to the degree of saturation times our void ratio. This is the holy grail of equations in geotechnical engineering, which is why I love geotechnical engineering, because it's the most easiest looking equation ever. It's not some crazy, like empirical based. But what this allows us to do is estimate any one of these variables based off of the things that we know. And by next week, you'll know how to calculate two of these: specific gravity and then moisture content. So we can easily find degree of saturation. We could easily find the void ratio or any of these variables just through this correlation. There's a few easy ways to remember it. Maybe you guys have already heard some of these before, but I'm going to write them up here. And yeah, so we can say, so SE equals, wait. Okay, so in its current form, GS is equal to SE. Way you can remember this is George Washington is equal to a soil engineer, which might not be true, but I didn't know him. It could be true. I don't know what yeah, George Washington sewage or soil engineer, or the way I was taught it is this form: SE equals WGS, which is sewage. SE equals WG. So that's whatever way is easiest for you to remember. George Washington is soil engineer, or sewage. SE equals WG. This equation will help you on the FE, and obviously help you in this class, like to just be able to recall this pretty quickly. But this equation is not something that's like given to you in your FE handbook, and it's not something that's going to be given to you on these exams. So use one of these pneumatic devices here to remember this equation. That will help tremendously. The cool case of this too is, sorry, notes are all over the place, but if it's the soil is taken from below the groundwater table, and if you remember, we assume that the degree of saturation is equal to 100%, which means in that case, our void ratio is just equal to this, which is really nice because our moisture content is easy to find. Our specific gravity is easy to find. And if you look in our lab syllabus, we don't do the void ratio test, the ASTM to do the void ratio, because it takes a lot of time and it's really difficult. So this is one of those shortcuts where if you have these certain scenarios, like below the groundwater table, degree of saturation is equal to 100%, then we can calculate the void ratio easily there. No, the SE equals WGS is not given to you. I know it's a hard one to remember.
What equation will be given?
On the exam?
Yeah.
You gotta wait till the exam. No, I'll share a formula sheet with you guys for that. What I will say, I keep showing this for a reason. Like these definitions are not going to be given to you. Yeah, so you have to remember this. You have to remember that. You have to remember 4 things, potentially 5.
But you're saying we need to remember them, but You need to not remember them, but associate those letters to what that.
Yes, yes. Yeah, which is why I think like thinking of the physical meaning of it is going to be the best fit. Like, what does it actually mean? Void ratio is tricky because it's two separate things, VS or VVVC, and moisture content. But degree of saturation, you shouldn't have to need to like have that equation. How much is it fully saturated, meaning all the water is fills up the void space or not? So, yeah, before each test. So like next week, at the end of next week, I'll share the I'll share example problems, like additional practice problems for the exam. And then also I'll give you the front page. I don't know if Dr. Islam did that or not. I think he just used my test too, but I give you the front page ahead of time so you know which equations you'll have. So use that as ahead of time. It's like, oh, I don't see this one. I should get used to memorizing it or something. Okay, but yeah, this one right here on the top right, this is like never given to you in geotech because it's so easy to memorize. To just memorize this using George Washington soil engineer or whatever. That's why if you look in the geotech lab, there's like a picture of George Washington with a hard hat on. That's the genesis behind that. All right, let's talk about void ratio now. So this is the next notes if you downloaded ahead of time, or if not, then we're caught up right here with the soil void ratio. Okay, so the void ratio is the volume of void divided by the volume of solid. And at the very beginning, I said moisture content and void ratio are the two most important like variables that we care about. And void ratio has a little bit more detail into it, even though it's just a very simple index. It's related to a lot more of like the geotechnical problems, like compaction, like soil mixing. And then also some of the soil settling, or like slowly compressing over time, where our structures are going to settle because we're loading them. So void ratio is a lot more related to the mechanics of loading, which is important. So void ratio is related to the actual mechanics of it. So there's a way of showing or expressing void ratio in terms of this value that's used quite often, and this is called relative density. Now it's really tricky because we've been talking about density and unit weight all the time, but basically what this is telling us is what is the current void ratio, or what is the current density in terms of the max possible ranges that are variable, that this specific soil can be compacted in. So one of the things we often find is we'll find the in situ void ratio. So just normal void ratio. This is that in situ. If you remember, I use that fun word that means in place or underground or as is. But then we'll do a test and see what is the maximum void ratio that it would have. And then what is the minimum void ratio that it would have. Now remember though, with void ratio, it's one of those weird like backwards kind of concepts where the maximum void ratio is corresponding to what type of density. Remember, high number of void ratio means what? Yeah, it means our volume of voids is up, which means our soil is loose or not dense. So our maximum void ratio is the soil in its loosest state or the lowest possible density. And our minimum void ratio is in the most dense state that we can make it. So it can be confusing right off the bat because we think max, we think of like the highest number or something, but really like it's the lowest density. So this is common only for granule soils, so only for sand. And we haven't really talked about like soil composition yet, but just know we would only really use this for sand and for silt. And we'll talk about reasons why like next lecture when we get into the differences between that. But when we're talking about clay, we would not use relative density for clay or cohesive material. So that E max, this is the minimum dry density. And the way we find this, there's an ASTM associated with this. We essentially take dry sand or dry silt or some type of dry material. We grind it up so it's all nice and airy and not stick together. And then we pour it or we fan it through a sieve into a mold with its known volume. So like essentially we have a cup and we just kind of sprinkle it through here and let gravity compact it. We don't apply any like compaction ourselves. You know, it's like doing a protein mix or something and just like letting it just like fill the container itself. The other side of it, the E minimum, this one is a hard value to obtain. This is compacting the soil into a known volume, but of course it's going to be dependent on the energy that we use. So like how much energy are we actually compacting into our soil? This one is a lot more difficult to obtain. So a lot of times what we'll do is be able to estimate a range of relative density that we need to apply at our site. And then we would be able to calculate or measure our max density, and then as well as our current density, or sorry, our current void ratio, and then find the minimum through that way. So our relative density, it is also expressed as a percent. But it's a helpful percent because it's a true percent. And hopefully from this equation, you can kind of see how it is that it's true. It's either 0 to 100%. But physically, what it does, it tells us in what percentage is our current or in situ void ratio, or just normal E, in the range of possible void ratio. So if it helps, like think of it as like a scale here. So like we have some scale of relative density expressed as percentage. So let's say we have 0 to 100%. And this is directly related to, sorry, this is a D. This is directly related to our void ratio scale, where maximum void ratio is this, our E min is going to be over here. Then our E max is going to be here. All right, let's try to squeeze this in here too. It's also related to our density, where our density minimum is here and our density max is here. So it's just a way of quantifying through 0 to 100% the max possible compactions. So relative density is kind of like a category in those terms where we have like descriptive terms in the industry. So if our sand has a relative density 0 between 15%, then we would call this a very loose sand, or vice versa, 85 to 100% very dense. So these are one of those like kind of catch-all terms that like geotechnical engineers, when we call a sand a dense sand, then we're expecting somewhere between 65 and 85% relative density. So another way of showing this is through this with gamma instead of our void ratio. So you can show it either way. This is also sometimes called density index. It's again just the percentage of it. Like this equation is just showing like what percentage of our range is. So this table here also shows how the type of sand has a different range of void ratio. And hopefully this is making sense. Like think of a well-rounded sand. Like let's say you have like a bucket of ping pong balls and you just fill that bucket up with ping pong balls. They're all rounded and they're all the same size. Like there's going to be a lot of void space in there, where if we had a bunch of like angular material or like bricks or something, they're going to be able to sit and have higher contact areas or more contact area and have less or more volume, more mass in the same amount of volume. So for uniform spheres up at the top, we see these general ranges of void ratios. And then you can see as we go down, we see the general ranges of max and min there for silty sand and gravel sand. And this is why like the angularity of soil as well as the gradation of soil is really important. You guys remember the term gradation from CE materials? No, you didn't. You guys never took CE materials? Oh, that's weird. I don't know. Maybe that's not for you. Okay, well, gradation is how the size of the particle is distributed. So is this soil, as we scoop it up here, are all the particles the same size? Are some of the particles small and large, you know? And like, but in some cases they might all be the same size. That's what I'm saying. Like it all depends on the geologic formation, the parent rock, all that stuff. So this is why we have these different ranges of void ratio. So for our void ratios here, again, this is our min is our highest density possible. And our max is our lowest density possible. And essentially why this is important, this range, is this shows potential of the void space to leave, which means if we think about this in terms of a phase diagram, being volume of solid and volume of void, let's say a truck drives over and compacts the soil a little bit more and rearranges these particles so our volume of void will decrease. What will happen to our total volume is our total volume will decrease too. So if we lose total volume, what will happen to our soil it will settle. So the whole site will settle because we are losing this total volume. And this is a really important thing in like design of structures, right? We don't want to have this beautiful site and have everything planned out. And then as soon as we build our heavy structure, the whole thing sinks down. That's called settlement. There's different types of settlement that we'll talk about in a little bit. So this depends on multiple things. It depends on grain size. It depends on grain shape. It depends on grain distribution. And it also depends on fine content. So fine content, for those who were in CE materials, the fine content is stuff that's below the 200 sieve in our stack of sieves. So for those who weren't, this just means a grain that is smaller than 75 microns, which is 0.075 millimeters. So really, really small material. This can greatly affect how our material will settle and move around. Now, there's a lot of correlations out here, and I'm just going to show these really quickly. This is really important in earthquake engineering. So we'll see a lot of stuff like from the 70s and the 80s and 90s when earthquake engineering first started coming up. But based off of these categories of well-rounded, so think ping pong balls, and then very angular, so think like, you know, on a popcorn, something very, very angular. We see these general ranges of void ratio. So Emax minus Emin. So if it's very angular, it's a very small range. The numbers don't really matter. I'm trying to show that this is the smallest range. And if it's well-rounded, we can see these here. So the general trend is the more angular our soil is, the smaller this range of anticipated void ratio is, which from an engineering perspective is good, because that's less variability in density or less variability in potential future settlement. These numbers don't really matter, but I'm just going to show you these because it's from that paper anyway. So you can see the range here. So these people too, this is again just a correlation between some of the things. So these guys, Kubrinovsky and Ishihara, this is big in earthquake engineering. California and in Germany or in Japan. So they were able to find these anticipated ranges where if we have E max, then we can calculate our E min, because remember, our E max is somewhat easy to find in the lab. There's a pretty standard method for it. Our E min is very difficult. So these are for different types of sands here, and this FC fine content, which means percent passing the number 200 seed, or the percent of our soil that is smaller than 0.75 millimeters in size. You'll also see this right here, PC. PC is the percent smaller than 0.005 millimeters, so much, much smaller. This is called our clay fraction. So these types of equations here, these are called empirical equations. Have you guys heard that word before? I think I've said it once. These are based off of real data, and then are fit like using a correlation or a statistic. So this is very common in geotechnical engineering because everything is site-based. You know, like our soil here is different than soil in Arizona, different soil than Canada. So we develop these relationships, these correlations based off of lab testing for our area. And so you need to think that there's all these ifs. We can only use this equation if we have this and if we have those conditions met. You'll see that a lot in geotech. All right, the last slide I want to show, and then we'll be done with this section at least of why this is important. This is one of those correlations of the void ratio range and the mean grain size, which is from our gradation test. So this is again one of those correlations. I don't know why this isn't here, but hopefully on yours it's actually printed out. One of these empirical relationships. This is an empirical equation, and you can kind of see, you remember from math, like how this fits. You have all this actual data. That's what these like little data points are. Actual measured data, and then you use a statistical function to fit that data, so then you can use it as a prediction tool. Okay, so at least we got through a good chunk of it. We'll talk about submerged density and its physical meaning, and then get into some of the grain size distribution stuff next week in prep for exams and all that stuff. So please don't forget the quiz. I will post it. I will go to my office this time, and I promise I will post it and test and make sure it works so you can take it. And then the homework should be viewable soon too.